Hi, everyone. Okay, let's see if this works. Can you guys hear me? The easiest way for me to find out if you can hear me is to ask, does anyone know how many stars someone got yesterday? If you can please send a message into the chat relay. The way to talk in this system is that you send messages in the chat relay. So you go to Zoom, you choose who to talk to, and you choose chat relay. Oh, it was Albert. Okay, I see. Fun, fun, fun. All right. Well, welcome back to our live solve. I actually hear an echo right now. Let me go and fix that. I'll be back in about 10 seconds. All right. The reason for the echo is because, as you can tell, I'm actually prepared to go up live with everyone else here as well. I'm over on that station as well. But anyway, first, welcome to our live solve. We're very happy to collaborate with National Math Counts because this is it's a great opportunity. It's a team-based contest actually, which gets lots of schools to participate, and then it creates an opportunity for many people in the school to work together to get better at math and to challenge themselves with hard problems. So we're very happy to collaborate with Math Counts again. And tonight, I'm going to be doing some of the problems too, because my equipment works, but I'm joined by two incredible people. And I'll actually let them introduce each other. Usually we go by alphabetical order of first name, but it looks like tonight's going to be challenging. So I'll just say, hey, Alan, why don't you introduce your other co-star?
Huh.
Wait, what?
Well, well, that's a little difficult. Okay, I guess I'll just go first. But yeah. We have two new people here today, and welcome back to our live solve. But I'm Alan, and that's Alan. So, just to differentiate ourselves, I'm Alan, he's Alan. So make sure you remember those. But just a little quick bio on Alan. So Alan is actually he's got a very impressive resume. Okay, so yeah, it's waving on the screen right there. He is the 2022 Math Counts Nationals winner. So he's very connected to this. If you've ever been participating in Math Counts, and he's also a 2023 MOP, which is the Math Olympiad Summer Program qualifier, and the IMO TSD qualifier. Which, if you've never heard of those things before, just think of like the top math competitions you can possibly think of in the nation. He's basically like the best of the best. And then he's not just a math guy, he's actually got a lot of other cool things. So he co captains the computer science club at his high school, and he also enjoys robotics, engineering, and wants to join the varsity soccer team like Messi, like Zydo Messi. So, yes, here's Alan.
Hello.
Alan Watt, yeah.
What's up, guys? Um, all right. I guess I'll go next. So obviously my name is Alan as well. So this is gonna be a little weird, but thank you so much, Alan, for the gracious introduction. That being said, now I'm going to introduce Alan as Alan. So this is gonna be a little weird, but let's see. All right. Now, Alan is another math guy. He's gotten first place in numerous state level and regional competitions, including this is why you guys are here, guys, including the Math Count State Competition. So, if you want to get good at math counts, you should pay a lot of attention to Alan. He's looking forward to participating in multiple events such as ARML, Mu Alpha Theta Nationals, and AMC. He is also an avid fan of speed math solving. That's like Math Counts Nationals Countdown. In addition to competitive math, Alan is a triple jump state championship qualifier. So he's really good at jumping. Uh, wait, sorry, that's not good. Okay, he's received numerous regional and national awards in writing competitions, and he's gotten first chair in several honor bands on the French horn, including qualifying for the Alabama All-State Band. He enjoys reading fantasy novels, playing soccer, and recording YouTube videos in his free time. So, if everybody could quickly test out the chat relay and just like verbal claps
Yeah.
for Alan real quick. Just
Yeah, say hi to
quickly in the
Alan
chat.
in the chat,
Say
please.
hi to Alan, please. Yeah. Uh, and that would be great. Okay, the chat is
Yes.
looking pretty active. We only had one online clap. Oh, never mind. Now we have two. Okay. Uh, more claps. Okay, nice. Um, yeah, I don't know. This is gonna be kind of a weird experience given that there's two Allens, but I guess we can get started now. So,
Yeah, okay. So, as you can see, everyone's putting answers down in the chat, and if you weren't here the first time, when you send answers and helpful, I guess, ideas or solutions, we get these little stars here. As you can see, a couple people are getting already. But with that being said, let's jump right into problem 20 from the sprint round. Okay, so we've got less problems to cover this time, but they're a little more tricky, so stick with us. Alright, if m and n are positive integers such that m to the n equals 64, what is the sum of all possible values of m plus n? So we're looking for, oops, my pen is a little small, but we're looking for all the possible values of m plus n. So maybe that means finding all the possible values of m and n, like respectively. And so, first of all, we know that m and n are positive integers. So that means numbers like 1, 2, 3, 4, and so on. Yeah, so, yeah, there are a bunch of different possible values of m and n, but what we can use to solve this is we're taking m to the n, so some number to some power. And breaking down 64 is actually pretty special because the prime factorization of 64 is just 2 to the 6th. 2 to the 6th. And so when we're solving this, so when we're solving this, well, here we already have one solution, right? So 2 to the 6th is already in the form m to the n. And in this case, m equals 2 and n equals 6. And remember, they're positive integers, so there's nothing tricky or nothing weird going on here. And when we know that 64 is 2 to the 6th, if we're looking for other integers that are in the form n to the n and equals 64, they're going to have to be some sort of like variation of 2 to the 6th. And so one other one we could try is, okay, so 3 doesn't work because there's no way to convert 2 to the 6th to 3 to something. But then 4 is going to work. So m equals 4 and n equals 3. And you can see how this works because 2 to the 6th equals 2 squared to the 3rd. And 2 squared is just 4. Okay. So that's another way we can find an m to the n. And then moving on. Yeah, so I see some explanations in the chat. So another way we can do n to the n is we can split up the 2 to the 6th into another form. So we had 2 to the 1st, which is 2, and then 2 squared, which is just 4. And now we have another one, which is 2 to the 3rd, right? And 2 to the 3rd squared equals 8 squared, which equals 64. And that also works. 64. So another solution we could have is that, and I'll put it down at the bottom here, is that m equals 3 and n equals 2. Okay, yeah. Yeah, so now moving on, we can't have a 2 to something greater than 6 inside because we only have 6 2's in our original problem, 2 to the 6th. So we've gone 1, 2, and 3, 2 to the 1st, 2 to the 2nd, and 2 to the 3rd. But 2 to the 4th won't work because 6 can't be divided into multiples of 4. Like, we can't take 2 to the 4th to any other number to get 2 to the 6th. So 2 to the 4th wouldn't work, and neither would 2 to the 5th. So our last possible case is just going to be 2 to the 6th to the 1st power. And this makes sense because 2 to the 6th is 64, and 64 to the 1st power is just 64. So our final case would be 2 to the 6th, so m equals 2, and n equals 6. So here are our 4 possible cases of m and n. We have 2, 4, 6, 3, 2, 3, 6, and 2. And we're looking for all the possible values of m plus n. So if we add these together, in our first case, we have 2 plus 6 equals 8. In our second case, 4 plus 3 equals 7. In our third case, 2 plus 6 equals 8. In our fourth case, 3 plus 2 equals 5. And so when we add all these numbers together, we get, yeah, so people are putting in the chat, we have 8 plus 7 plus 8 plus 5. 8 plus 7 plus 8 plus 5. And when you calculate this out, you should get, if we did the math correctly, 28 as our total sum of all the possible values. Yeah, just confirming if that is the correct answer. Okay, yeah, so that wasn't actually correct. But, guys, sorry, I made a little mistake here. Alright, so looking at these numbers, let's go back a little bit. Sorry, I made a little mistake here. Okay, so what we did wrong is, yeah, the answer is 90, but our third case, m would equal 2 to the third. And 2 to the third is actually 8. I just forgot to write that out there. But 2 to the third equals 8, and n would equal 2. 8 squared equals 64. And then for our fourth case, m is 2 to the sixth, which is 64. And then n is going to be 1. But yeah, we just got a little mixed up with the numbers there. And then when we add this up, we're going to get our actual answer, which is 8 plus 7 plus 8 plus 2 equals 10. 64 plus 1 equals 65. And that equals 15 plus 65 plus 10, which equals 90. Yeah, so 90 is our real answer. Sorry for that little misstep there, but all right. Now,
No need to
Alan,
apologize. These things are getting hard. The questions are getting hard at this point. Actually, I don't know. Oh my gosh, Alan, the other Alan, did you see any faster way to do this? I'm not sure I saw a much faster way myself.
To be honest, I think Alan, or okay, that's getting really confusing. I think Alan with one L, or the other Alan, I think that was a really good solution. I think that was honestly the fastest solution that I
Yeah.
saw too, because you have to somehow get all of the cases, and at some point you just have to compute everything, and it's not great, but you have to kind of suffer through it. So
Yeah, seems like it to me too. Actually, I should also say, when you say Alan, everyone knows who you're talking about, because otherwise you say me or I, right? The only person who has trouble is me when I say Alan. All right.
oh,
that is true.
Now, Alan
Okay.
and it doesn't even help if I say Alan from Alabama. You're both from Alabama.
indeed.
So, so anyway, I'll say Alan with 2 L's. Why don't you take the next question? I'll jump in on the third one.
Oh, I should also say, like Alabama also starts with AL. So this is a pretty funny coincidence. I don't really know what happened there. Okay. I guess I'm on the big screen now, so what's up, guys? Let's move to question 21 and see what's happening here. Okay. Let me just quickly read the question out because this is kind of a big English question. Okay. Adam has 5 different sized matchsticks whose lengths are positive integer numbered of centimeters. No 3 can be arranged to form the sides of a triangle. What is the least possible sum of the lengths of all of Adam's matchsticks? Okay, so at least for me personally, when I look at this question, I always like to look at what the question is asking us for. So what is the question asking us for here? Well, it's asking for the least possible sum of the lengths of all the matchsticks. So it's asking for the least possible sum of all the lengths. So what that basically tells me is that intuitively, I want all of the matchsticks to be as small as possible. I want all of the matchsticks to be as short as I can make them. Okay, so how do I make all the matchsticks as short as I can get? Well, now I'm going to ask you guys a question, if you don't mind. What is the shortest possible matchstick that I can get? If you guys could just put it in the chat. What is the shortest possible matchstick that I can get? And no pressure, just take your time. Yeah, Albert says, okay, everybody's saying 1. That was quite fast. Okay, so good job, everyone. It is 1. Okay, now, because obviously the first one, the smallest possible is just 1. Now, here's an additional question for you guys. What's the second smallest matchstick that I can get? If 1 was the smallest, what's the next size matchstick that I can get? Yeah, Alex says 2. Albert says 2. Everyone's saying 2. Unfortunately, okay, actually I won't say that. But yes, it's 2. It is 2. Now, you guys can probably see what's happening. Yeah, Nicola actually says 3 for the next one. Ming Ming says 3. Everyone thinks the next one is 3. I didn't even have to ask you guys the question. Okay, that's good. So the next smallest matchstick we can get after 1 and after 2 is going to be 3. Okay, now I have one more question for you guys, and then I won't ask any more questions for the sake of time, I suppose. But if I told you guys that the next matchstick was 4, could you guys tell me why 4 does not work? Could you guys tell me why 4 does not work? Why does 4 not work here? And no pressure, just take your time. Yeah, 2, 3, 4 makes a triangle. 2, 3, 4 makes a triangle, and we see here that no 3 can be arranged to form a triangle. So 4 doesn't work because 2, 3, 4 is a valid triangle. So the next one is 5. Now, I'm just going to finish up the question here. By the same logic, notice that the fourth one has to be a 5. So what can the fifth one be? Well, the fifth one cannot be a 6 because 3, 5, and 6 is a triangle. Furthermore, the fifth one cannot be a 7 because 3, 5, 7 is a triangle. That means that the fifth one has to be an 8. And why does 8 work? Well, because 8, it turns out, is the smallest length that is big enough. Because when you have 8, then the largest sum that you can get with anything smaller is 3 plus 5. And 3 plus 5 is not going to exceed 8. Or 3 plus 5, yes, is not going to exceed 8. And so 8 is valid. And yeah, so the answer is 1 plus 2 plus 3 plus 5 plus 8. And that turns out to be equal to 19. So hopefully that made sense to you guys. The answer is 19. And yes, this is the Fibonacci sequence. So good job if you spotted that. The answer is 19. All right. Yeah, hopefully that makes sense to everyone. I think Professor Loh is going to take the next one, but he's currently...
Hey, okay, I think I'm
Oh,
back
okay.
here now. Am I here
Nice.
now? Hopefully I'm here now. Just can't see anything. Hi everyone. I'm gonna try to make my computer work. Okay, so I'm gonna jump in. I apologize. My chat relay doesn't work as well as theirs because they have the cool setup and I have an old one. But I'm gonna try to do the next question. Oh, is that the next question? Is this what we're on next? Yes, I think so. All right. So suppose x is a real number such that 2 to the x equals x plus 3. What is the value of the expression below? Whenever I look at something like this, the first thing I want to know is, do I need to actually figure out x? I think I do because it appears up there and also down here. And it doesn't cancel. So I actually need to know what x is. But the good news is I don't really need to know what x is. I need to know what 2 to the x is because I'll write the same thing up there and down there. Well, when I see an equation like this, I just use guess and check. Unfortunately, I'm really sorry. Your chat's not appearing on my screen, but I can actually see the messages you're sending. So I'm just looking at the things you're sending at the same time. But when I look at these kind of expressions, I've got to do some guess and check. The good news is powers of 2 get really big really fast, so I probably don't have to guess that far. So let me try. What if x equals 5? If x equals 5, then I get 32 equals 5 plus 3, 8. No, it doesn't. That's not true. So let's try a different value. 5 was too big. What about x equals 2? Then I get 4 equals 5. We're getting closer. Looks like I went too far. What if x equals 3? First of all, that's not true. What if x equals 3? Wait, this is no good. Then I get 8 equals 6. Oh no, I can't use guess and check. It says a real number. It doesn't work. So actually, I should have seen that coming because these things flipped in order. Like that one's bigger, 32 is bigger, now 4 is smaller. So that's no good. And already over here, I see I got in trouble. So I got a real number. Yuck. Is there an easier way to solve this? Oh, all right. I'm going to try to do a different kind of simplification. So by the way, these are all called live solves. That means that we don't actually know how to solve the problem before we start. So you can see how someone thinks about this. Real number, guess and check, no good. So now I'm going to try to use algebra. So I want to do maybe a substitution. If I look at this, is it better to replace 2 to the x here by x plus 3? Or replace down here by 2 to the x? I'm actually interested in replacing down here by 2 to the x because I think something will happen with subtracting exponents. 2 to the 2 to the x divided by 2 to the x. Aha. 2 to something divided by 2 to something else is 2 to the difference of powers. So this is equal to 2 to the power, 2 to the x, and then minus x. Ah. Why do I like that? I'm smiling. I'm smiling because 2 to the x minus x, I actually can figure out what that is. Look over here. 2 to the x minus x is equal to, you can type it into the chat, maybe you can beat me to it. I can still see what you guys are typing. So this is 2 to the x minus x. That's equal to 3. So in that case, I can put that here, and I get 2 to the 3. I think it might be 8. Is it? It worked. Okay. Back to Alan with 1L.
Okay, so now that we've heard from, we've heard from Alan, and Professor Loh, we're coming back to me with a new one. All right, so problem. Let's see if it'll load. Yeah, okay. So problem 23. All right, when the square root of 6 plus 2 root 5 is written in simplest radical form as a plus root b, where a and b are positive integers, what is the value of a plus b? So we have another sum here. And we're given a couple things here. So we have root 6 plus 2 root 5. And this radical is just a little weird, right? Because, we've got a big radical and then a radical inside. Yeah, and if you look at this radical inside, it's root 5. And like Albert said, it's not a perfect square. And so, unlike root 4 or root 9 or some of those other things, we can't get a simple integer that'll help us solve this problem. If we were to take the square root of 5, we might get something like 2.2, some decimal that isn't fun to work with. So maybe we need something else. Well, the problem says that we can rewrite this radical in the form a plus root b. And so let's do that. Let's say root 6 plus 2 root 5 equals a plus root b. And so now with this equation, I don't really like radicals or decimals or those kind of things, so I just want to get rid of them as fast as possible. And the easiest way I can see to do that is to get rid of this first outside radical, we can maybe square this whole equation. And so if you take a radical and you square it, it just simply removes the radical. And we get 6 plus 2 root 5 equals, let's see, a plus root b squared. if we write that out a little wider, we need to multiply each term inside. So we get a squared plus root ab, and then another root ab, plus b. Okay, so now we have this new equation, 6 plus 3 root 5 equals a squared plus 2a root b plus b. And this one's a lot easier to work with because we only have single radicals this time. And what we're noticing here is that to find what a and b are, we can match up the non-radical parts with the non-radical parts and the radical parts with the radical parts, right? Because that'll make it a lot easier to see what's going on. And if we do that, let's do it in yellow here. We get a squared plus b equals 6. And then the radical part, 2a root b equals 2 root 5. Alright, and then for this bottom one, we can just divide by 2 on both sides and get that a root b equals root 5. And so, okay, now we have an interesting problem here. We've got a lot of variables and numbers, but the solution is not very clear. But if we look at this bottom equation, a root b equals 5, the easiest thing that stands out to me here is that root 5 is the same thing as 1 root 5, and maybe we can match up the a and the b. So we could say a equals 1, and then b equals 5, because b is another radical, and 5 is also another radical. So when we do that, we get a equals 1, and b equals 5. This makes sense because the problem tells us that a and b are both positive integers. And then when we plug this into our top equation here, we see that a, 1 squared, plus 5 equals 6, and that makes sense. So a equals 1 and b equals 5 actually works for both of these equations, which is exactly what we're looking for. And they satisfy every part of the problem. So if we go all the way back up and check, we have that this whole thing, root 6 plus 2 root 5 equals a plus root b. And since we know a and we know b, we know that a plus root b is just 1 plus root 5. These are the same things, so we just plug in a and b. And so, as a result, we're looking for a plus b, and we get that a plus b equals 1 plus 5, which gives us a final answer of 6. And notice one quick thing, that you didn't have to go back and figure out what a plus root b is, because once we figure out a and b, we can just go ahead and add. So whenever you can, you're going to want to skip steps, and I think that'll help you a lot when you're trying to solve MathCounts problems really fast. Okay, but yeah, with that, I'll hand it over to Alan with 2 L's this time, and see what he has for us on the next problem.
All right. So, right here, I got the next question. Actually, thank you, Alan. Thank you, Alan, so much for that previous explanation. And thank you for letting me take the next one, because, teamwork makes the dream work. Okay, so here's the next question. How many ordered pairs of positive integers, m, n, are there, with n less than or equal to 10, and where this inequality right here holds? So what is this inequality saying? 2 root 3 is less than or equal to m over n is less than or equal, is less than 1. All right, so how do we do this question? Okay, so this is the idea that I'm going to suggest to you guys. When I look at this question, what do I see? Well, what I see is that I want to put in an example, right? Let's say, I don't know, what's a good example? Like, I don't know. Oh, that's not a good 2. Okay. Let's say I put in 2 over 3 is less than or equal to 5 over 7 is less than or equal to 1. So what I've just done here is I've put in an example for m and n. And what do I see when I look at this? Well, what I see is that 5 over 7 is hard to calculate. 5 over 7 is hard to calculate. Why is it hard to calculate? Well, because n is in the denominator. N is basically being divided. And when you divide something by n, the result is that you get this really annoying, hard to calculate decimal. And so what we need to do is we need to multiply the original inequality by n. That original inequality needs to be multiplied by n, and we get 2 to the third n less than or equal to m is less than n. And now you can see that this inequality is much easier to work with. Okay, so let me go ahead and erase what I've just done. And now we can just work with this inequality. Okay. Erase, erase, erase. Okay, cool. Now I'm just gonna finish up the question real quick because we do need to go a little fast, I guess. So apologies if it goes a bit quickly, but let's do this. So n is less than or equal to 10. That is the second condition that I have. So what does that tell me? Well, that tells me that n is going to be something in the following set, 1 through 10. Okay, yeah. As Professor Loh is telling me, it's bash time. So, guys, hang tight. It's gonna be a fun ride. All right, let's do this. So, n equals 1. What do we get here? We get 2 over 3 less than or equal to m is less than n, is less than 1. This doesn't work. N equals 2. 4 over 3 is less than or equal to m is less than 2. In this case, doesn't work. All right. And when I say doesn't work, I'm doing the part about not working in my head. So hopefully you guys can follow along. But basically, for example, when I say that n equals 2 doesn't work, I'm just saying that there does not exist an integer m within these two bounds. Like nothing is going to work there. Hopefully you guys can follow along on that. And apologies if you can't, but just try to look back if it's going too fast. No worries. Okay, so n equals 3. This is the bound that we get. In this case, we get one solution, m equals 2. N equals 4. Let's see, 8 over 3. And this. Okay, so we're trying to speed up a little here. There's one solution, m equals 3. N equals 5. Let's see, it's 10 over 3 is less than or equal to m is less than 5. In this case, there is only one solution. All right, and we're approaching the end. N equals 6. We get 12 over 3 is less than or equal to m is less than 6. There's two solutions here, 4 and 5. Okay, let's see, where do I have space? N equals 7. 14 over 3 is less than or equal to m is less than 7. What happens here? Okay, 5 and 6 both work. Okay, n equals 8. We get 16 over 3. Okay, this is getting a little tiring, guys. This one has two solutions as well. All right, I should be almost done here. So really, what I'm doing here, if you guys have been following along, I've just been testing out case after case. I don't actually know if there's a faster solution than this. So I really apologize to you guys if, it's a little tedious. But this is the final case. 20 over 3 less than or equal to m is less than 10. And in this final case, we get 7, 8, 9. There are three solutions in the final case. All right, so every single circled number on my screen is what we want to add up. 3, 6, 7, 8, 10, 12, 14, 15. Answer is 15. All right. That's done. That's done. That's done. And let's see. It's 15.
Whoa.
Wow.
Okay. Yeah, good job, Alan, with two L's. I was chatting with our instructors as they were doing this. I was like, how does anyone finish this sprint round in 40 minutes? This is crazy. But I think I saw something people noticed. They noticed a bit of a pattern that was coming. So Alan was limited on screen space. That's the only reason it was like running around the screen. If you were going along in order, you'd have noticed it was 1, 1, 1, 2, 2, 2. So presumably it has some pattern. Probably has something mod 3. There's a 3 there. I'll leave that for you guys to think about. But now I guess I go on to the next question. We're going to jump ahead because our time is a bit short. So I'm going to jump to question 28 just because we want to punish ourselves. So I'm going to do 28. Alan with 1L is going to do 29. Alan with 2L's is going to do 30. But we're all going to work together because I might need you guys' help. Okay. So let's see. I'll go to 28. What's 28? Whoa! Okay, what's the first non-zero digit of that? Okay, okay. Now that's kind of interesting. So I know what this is approximately. So I know that this number here is going to be approximately 75, right? So root 75 squared is 75. So it's 75 point something. I didn't know that middle school students learn this stuff though. See, all right. I know it's around 75, so I'm gonna factor out that 75. If you factor out what I mean by factor out the 75, I'm gonna factor out 75 squared. So from the inside. So that gives me square root of 75 squared times 1 plus 1 over 75 squared. Why did I do this? I did this because, and I don't know if this is the most efficient way either, but I'm going to pull out the 75 squared as uh, square root as just 75 times square root of 1 plus 1 over 75 squared. And now I'm going to do something which is actually from calculus. But there's an approximation that the square root of 1 plus x, this is actually approximately 1 plus x over 2. Let me ask, Alan and Alan, do I have that right? Is that right? Is that the Taylor series?
Uh, I think okay. So oh wait, my screen is still on this mess. Okay, hold on. Yeah, that looks right. I
Is that
think I
right?
for
So there's something called the Taylor series. It's where you take the derivative. I can't believe we're talking about this on a middle school live stream, but the derivative of the function 1 plus root 1 plus x is actually 1/2. Yeah, so this is actually an approximation. I'll tell you, I actually came across this by so I happen to know this thing is true, but I also came across this idea when I was doing middle school math counts because somehow I noticed that there's a factor of 2 that appears. For example, if I take 11 squared, it gives 121. So like from I guess I can tell you how you can think of this. The way you can think of this is if you square both sides, you might see, then you'll see why the half comes in. Why? This is not a proof why, but this is how you could think of it. If you squared both sides of this particular approximation, that would be telling you that 1 plus x is approximately 1 plus, what's 1 plus x over 2 whole things squared? It's the first thing squared plus 2 times the first times the second, which is just an x, plus the second thing squared. Now, you might say x squared over 4 looks big, except that think about what x is. So when we're thinking of the mistake, how much mistake are we making? I'm about to apply this where x is 1 over 75 whole things squared. If I do x being 1 over 75 squared, think about how big x squared over 4 is. It's like almost nothing, okay? So if I do this approximation, I'm going to get that this is approximately, in applying the approximation, I'll get that this is approximately 75 times 1 plus 1 over 2 times 75 squared. This approximation, if I get something which is, you see, I need to get the first digit after the decimal point. If I got that this is very close to like something 0.39, I would be scared. Because the 39, I don't know if it's going to be a 3 or a 4. Let's see what we get though. This is going to be about, now I'll write equal sign, because that was approximately, but this is equal. This is equal to 75 plus 1 over 2 times 75, which is 75 plus 1 over 150. What is 1 over 150? Now I have to think. Oh, wait, that's very small. That's less than 1 over 100. So this would be like 75.0 something. Now I want to know, do I need to subtract something? I think the next term is not going to be that much. So, oh no, wait, I'm not reading properly. I'm in big trouble. The big trouble with these problems is that you need to read. So I had just figured out that the digit is 0. Now I need a non-zero. Yikes. Okay, back to thinking. So it's going to, oh, okay. Now I'm going to change strategy. So this won't work. So this strategy over here will tell me the first digit after the decimal point, and the first digit is 0. Great. Now we got to do some more work. So then if I go to think about it again, I mean, I went backwards. This is not the actual answer. I went backwards because I don't want to be shown the answer. Let's go and think. What we're trying to do here is we're trying to do square root 75 squared plus 1. Okay. So if I want to think of that, I have a sense that this is going to be, I have 75 point, bunch of zeros, don't know how many, and then some digit, x. Squared is supposed to be exactly equal to 75 squared plus 1. Okay. Well, if I go and expand this, wait a second. I'm going to go back here because my 1 over 150, maybe I can still use because I have some error afterwards, but let's see what is 1 over 150. What is that? I haven't done these math competitions in long enough, so I don't know off the top of my head what is one. Oh, I know how to do it. 1 over 150. I'm going to compare that to 1 over 100. 1 over 150 is sort of like 1 over 100, but not exactly. It's times 2/3. Is that fair? Because 1 over 100 is, well, 100 times 3 over 2 would give me 150. So in that case, I actually know what that is as a decimal, because that's going to be as a decimal point. So I'll write 0 point. So it's 0 point. It would be 6666, except I have 2 extra zeros because of the 2/3 would be 0.666, and I go divide by 100. So I'm going to get out of this is approximately 75.00, and then like some sixes. There will be some error. The size of the error is going to be of the next order term, which is something squared. But I see I'm at a 6, so I'm already satisfied because I don't think that's going to be enough to change this digit. So I'll put as my answer 6. Yes, we got it. I don't know if there's a better way. Alan, do you have any ideas?
I think that might be the best way because with decimals, it's always very bashy and tricky.
All right. Well, in that case, Alan
Yeah,
with
I
1
agree.
L. Next one.
Yeah.
And Alan with 2 L's, you're going to be stuck with the last question.
Oh,
Okay, guys, so we are nearing I guess near the end of the sprint round, and oops, wrong problem. But yeah, so these are gonna get kind of tricky, but we have that. Our question is, how many ordered pairs of positive integers, a and b? So I think like a bunch of these questions have been positive integers a and b, so it seems to be like a theme. But how many satisfy 7ab over a plus b equals 2025? Okay, so if we just tried some numbers like, well, what if we wanted the bottom to be 1 in like 2024, and the top would also be that? Okay, this is very strange because like just trying to plug in numbers, it doesn't seem like I'm getting anywhere because most of these numbers are going to end up as this thing as a fraction, and the rest of them are also going to become, I don't know, just not work out. Oh, but Andrew tells us we could use something called Simon's favorite factoring trick. Okay, so we're gonna get to that a little bit later, but just keep in mind that's a very interesting fact, and that's gonna be very helpful. But so with any fraction, we want to get rid of the bottom, right? So we can multiply by a plus b on both sides. On the left side, we get 7ab equals 2025a plus 2025b. Okay, now, we still have a bunch of big numbers on both sides, so let's move this part to the left side. How about that? And we'll get 7ab minus 2025a minus 2025b equals 0. And like people were saying, oh yeah, so you can use Simon's favorite factoring trick. And what that is just a quick overview. You won't go into like proving it or anything, but a quick overview. That basically says when you have something like AB plus, let's just say XA plus, or YB equals 0. You can basically factor that into A plus Y and B plus X. So yeah, in the chat, correct me if I'm wrong about this because it's been a while since I've used this formula, but you can basically factor it into this and, oh yeah, equals XY. So you basically, this X and the Y, the coefficients of A and B, multiply and add on the right side. Yeah. Okay, but the issue with this problem is that we have our coefficients of X and Y, they're negative 2025, and we have A and B, but the AB doesn't have a coefficient of 1, so that makes the problem a lot more difficult to solve. Alright then, how about we try a different thing? Okay, so we notice that 2025 is 45 squared, and maybe these square terms will help us solve this, but one solution we could take is we could divide by 7 to make the AB have a coefficient of 1, because in that case we could use Simon's favorite factoring trick to solve this problem. Okay, so if we do that, this is going to take up a lot of my screen, but if we divide by 7 on both sides, we get AB minus 2025 over 7A minus 2025B over 7 equals, it's going off the page a little, but equals, let's see, on the side we would have x times y, so x times y is 2025 times 2025, which is 2025 squared, or 45 to the 4th. And then when you factor this, you get a minus 2025 over, oh, but there's a mistake, Okay, so remember, on the right side, we're multiplying the coefficients x and y, and we get 2025 over 7 squared, but that's going to get 2025 squared over 49, which makes all of it way harder to solve. So yeah, let's just go back and try this problem a different way, because it's getting a lot more confusing. All right. Okay. Okay, so yeah, this is a messy problem. So as we noticed before, 2025 is 45 squared, and sometimes you can use squared terms to find easier factorizations. So right now we have a 7, which isn't very easy to solve. It's not a squared term, and there's no square root of 7 or a good way to factor it. But if we multiply this 7 by 7, it becomes 7 squared, which is a lot easier to factor. So when we multiply by 7 on the whole equation, we get 49AB minus, let's not multiply this out, let's just keep it minus 7 times 2025A minus 7 times 2025B. And then this 0 is just going to become, the 0 over here is just going to become, it's going to stay 0, because 0 times 7 equals 0. And yeah, now what we have here is something we might be able to factor. So let's look at these first two terms. They have in common 7a, and if we factor out 7a, we get 7a times 7b minus 2025. And then we have a last term over here, which it doesn't seem like we can factor it, but there's a trick you can do, and I think some people in the chat mentioned it, but it's kind of like completing the square, or adding or subtracting something on to make it easier to factor. And so we already have a 7 and a b and a 2025, which looks really similar to this part. So let's try to make it look similar to that. Okay, so what can we factor out to make this part 7b? We can factor out a 2025, right? Because if you take that out, then this term is just going to be left with 7b. And then the other issue is that if we want to make it look exactly like this parentheses, it's going to have a negative 2025. So we're going to need to have it look like a negative 2025 in here. But that would mean, if we expand this, we have negative 2025 times 7b times negative 2025. And this section, this specific part, the negative 2025 times the negative 2025 is something we don't have. So why don't we add that on to our original equation? So if we add that on, I'll write it over here. So our original equation becomes 49ab minus 7 times 2025a minus 7 times 2025b plus 2025 squared equals, remember, when you do it on the left, you have to do it to the right, so we add 2025 squared on the right side as well. This whole bubbly thing simplifies to this. Okay, so now that we have that, we can finally do a more, I guess, elegant factorization, and we can factor out this 7b minus 2025. 7b minus 2025, and we get the stuff that's remaining is the 7a minus 2025 left. And so we write that out. This is what our whole thing factors into. And then this equals 2025 squared. Now, we have two numbers that multiply to 2025 squared. So these two numbers must be factors of 2025 squared. And so, how can we do this? Well, let's break down 2025 squared even more. So 2025 squared equals 45 squared, because 45 squared equals 25. 45 squared like this, and then you can rewrite that as 45 to the fourth, and then break that down even more to say 45 to the fourth equals 3 squared to the fourth, so 3 to the eighth, times 5 to the fourth. So now we're looking for two factors that multiply to this number, 3/8 times 5 to the fourth. And let's see. Well, if each of these numbers were, say, 45 squared, that might work. Or, yeah, if each of these numbers equal 25, that might also be a solution. And I think Ming said, yeah, there's 45 possible ordered pairs because 3 to the 8th times 5 to the 4th has 45 factors. We have 9 times 5 equals 45 factors. And since we know this whole thing is 2025 squared, we could say, what if each of these parentheses equations were 45? Okay. So if each of them are 45, 7b minus 2025, 7b, I'll do it up on the left here. 7b minus 2025 would equal 2025. Then 7b would equal 4050, and b would equal 4050 over 7. Okay. Just looking at it, I don't think this divides evenly. I think it's just, we just get left with a fraction, which we can't do that, right? Because we're looking for positive integers a and b. Yeah, so this problem is even more confusing than it already is, but let's just keep going. I think we'll be able to find something. All right, so, okay, we need b or a, either one, to end up being a positive integer. And it looks like in most cases that doesn't work. So how are we going to solve this? So 7b minus 25, 2025 needs to be a factor. And so, b needs to be an integer. Okay, so, well, how can we do this? First of all, we need it to be positive. So what's the minimum value of b that we could have to make it positive? Let's see. Well, 2025 divided by 7. Let's do a little bit of mental math here. 2025 divided by 7 is, be easy to write it out. It's going to be about 289 with a remainder of 2. And so 7 must be at least 290, or b must be at least 290, and with that we'll get 2030, so a little over 2025. So the minimum b can be is 290 to make this whole thing a positive factor. And then with that, it just continues. So if b is 291, for example, we'll have 2037, and then so on, so on. As b increases, we increase by 7 and 7 and 7. And so, after doing this, okay, 290, 2030, we can basically simplify this, because if 7b at minimum, and let's see, is there any, okay, so 7b at a minimum is going to be 2030, and then 2030 minus 2025 is just 2030 minus 2025 is just going to be 5. And so this whole thing, if we increase b by 1, that 5 will become a 12, and that 12 will become a 19. So as you can see, as we increase b, 2000, whatever 7b is minus 2025 is just going to go 5, 12, 19, and so on. 5, 12, 19, and so on. Okay, so what we're looking for now is this 5, 12, and 19 is just a different representation of 7b minus 2025. And we're going to need that to be a factor of 3 to the 8 times 5 to the 4th. So for that to work, it needs to be made up of, and we got an explanation on the screen, but yeah. So that needs to go into 3 to the 8th times 5 to the 4th. Okay, and if we continue along this path, and my screen's getting a little cluttered here, but 5, 12, 19, 26, so on. Essentially, yeah, so it's going to be kind of hard to figure out. Yeah, this is a pretty long problem. Okay, it's going to be pretty hard to figure out exactly how many numbers equal this prime factorization. And I'm getting a little stuck here. So, Alan and Professor Loh, do y'all have any ideas of how we can continue this problem?
Yeah, actually, the other Alan and I are discussing this as you're going, and I'm saying I don't see a great way to do this either. But the other Alan seemed to have some ideas. Do your ideas work, Alan?
Yeah, so I haven't actually fully molded out my ideas yet, but if you guys will just bear with me, Alan, do you mind if I follow along from where you left off real quick?
Yeah, go ahead. I need more screen space anyway.
All right, so basically, let me just recap what Alan did so far. Basically, the progress that has been made so far is that we have simplified the equation into something of the following form. We have simplified our original equation into this nicer looking equation right here. This is our new equation. So that's what we have right now. And so how do we solve the question from here? Well, another thing that Alan actually did on his screen was, and this is going to be my first step, is we take this rightmost side and we need to prime factorize this rightmost side. So let me do that real quick. What do we get when we prime factorize the rightmost side? It turns out we get 3 to the 8 times 5 to the 4. Okay, so obviously we still need this very, very annoying product on the left-hand side. And this is actually going to be the hard part. So everything I've done so far is like the easy part. So you guys all right, we need to lock in now because this is going to be pretty tough. As you guys have already seen. I mean, this is just a hard problem. All right, let's do this. So what I'm going to do is introduce a concept which may be unknown to you guys. It's turns out it's very simple. So it's this concept of modulo. So if you've never heard of what modulo is, it's basically the same thing as remainder. So, for example, if I say that I'm taking a number and I quote modulo 7, I'm really just taking the number's remainder divided by 7. So hopefully that makes sense. So let me erase these definitions real quick because as Alan has demonstrated, this question doesn't take a lot of space. So I'm going to try to conserve as best as I can. All right, so what is And I'm going to ask sort of a rhetorical question here, and you guys can put your responses in the chat, but I'm just going to go ahead and continue. What is 2025 modulo 7? Well, it turns out this is equal to 2. Okay, 2025 modulo 7 is equal to 2. Why did I just do that? Well, here's a follow-up question. What is 7a minus 2025 modulo 7? That's my follow-up question. What is that modulo 7? Well, it turns out that modulo is actually sort of associative in a sense. What do I mean by associative? I don't know if that's the right terminology, but it means that I can take 7a modulo 7 and 2025 modulo 7 separately. I can take them separately and then subtract them to get 0 minus negative 2, or sorry, 0 minus 2 modulo 7. That is equal to 5. Why is it equal to 5? Well, because negative 2 modulo 7 is equal to 2 plus 7. So modulo, I should clarify, works in the opposite direction as well. It's not just remainder. You can also add 7s to get to where you
You
want
mean
to
minus
be.
2 plus 7.
Oh, sorry. Yes, minus 2 plus 7. So what I have essentially done here, thank you, Professor Loh. I actually missed that. But what I have essentially done here is I have demonstrated that 7a minus 2025 is equal to 5 modulo 7. Okay, so why is this important? And this is really the crux of the problem. This is where I'm getting to. So I'm going to move on to a new slide real quick where I have a lot more space to work. And this is actually, like, I have done, let's say, 80% of the question at this point. Everything else I'm about to do is going to make, hopefully, a lot of sense. So 7a minus 2025, 7b minus 2025 is equal to 3 to the 8 times 5 to the 4. This is what we have. We also know that this number here is 5 modulo 7, and that this number here is also 5 modulo 7. Okay, so what is the final step that we need to do? Well, here is another rhetorical question for you guys. And by the way, I know that we're 2 minutes over time, so apologies about that, but if you guys could just bear with me for a second. I should be done in the next like 5 minutes, which is kind of crazy to think about considering how hard this is, but let's do this. So, rhetorical question for you guys. What is the prime factorization of 7a minus 2025? What is that number's prime factorization? Well, that number's prime factorization is 3 to the x times 5 to the y, where x is in the set 0 to 8, x is in the set 0 to 8, and y is in the set 0 to 4. So, let me now restate what this simplified question is. The simplified question is, I want a number of the form 3 to the x times 5 to the y, where x is in the set 0 to 8, where x is in the set 0 to 8, y is in the set 0 to 4, and 3 to the x times 5 to the y is 5 modulo 7. This is what I want. Okay, so now I am finally ready to solve the question. So, and this is actually where I need to sort of work on it for a second, because I think this is the part where we might have to do a little bit of bash. Yes, I see people saying this for sprint is crazy. Yes, I probably would not have gotten to this question. Actually, just checking in with you guys real quick. Is everything making sense so far? Because like I think checking in usually takes some time, but I just want to make sure. Is this making sense? Because I know this can be very complicated. Okay, yes, I would have skipped the question. Yeah, I would have skipped this question as well. Okay, just stop me if something doesn't make sense, and I'll try my best to re-explain it. But let's continue. So, 3 to the x times 5 to the y needs to be equal to 5 modulo 7. So, okay, I understand how to solve it from here. Let's completely erase what I did up here because, right, we've moved on. We're on to the final step of the question. We don't need anything up here anymore. All of this, gone. That's gone. That's gone. That's gone. I don't need any of that. This is what I have. This is the last thing I need to do. How do we solve the question from here? Well, again, we know that modulo actually has this interesting property where 3 to the x times 5 to the y modulo 7 is actually equal to 3 to the x modulo 7 times 5 to the x modulo 7. Or sorry, 5 to the y modulo 7. So I can basically split the modulo in half. And again, modulo means remainder here. So the remainder of 3 to the x times 5 to the y divided by 7 is equal to the product of the two individual remainders. Okay, why is that useful? Well, it's actually extremely important because this will basically solve the problem for us. Because what is this first part? It can be 3 to the 0, 3 to the 1, anything up to 3 to the 8. What can the second part be? 5 to the 0, 5 to the 1, anything up to 5 to the 4. And now, you guys hopefully can see where I'm going with this, because we want to choose one of these remainders, we want to multiply that by one of these remainders, and we want that final result to be equal to 5. That is what we're looking for. Okay, now we just made more progress. So let's remove that. This is what we have now. We want to choose one of the remainders on the left, one of the remainders on the right, and get 5. So how do we do that? Well, this is where it gets sort of interesting. So I'm going to actually explicitly compute each one of the remainders, 3 to the 0, all the way to 3 to the 8, modulo 7. And I'm just going to go ahead and do this part on my own just for the sake of time. It's 1, 3, 2, 6, 4, 5, and 1. And I believe that the last one is going to be, or actually no, 1, 3, 2. These are the remainders that I have for 3 to the 0 to 3 to the 8 modulo 7. I apologize if this is getting a little complicated at this point, but hopefully everything makes sense so far. I know it's pretty tiring, but if you guys could bear with me just for a little longer, we will be done very soon. Now, 5 to the 0, 5 to the 1, all the way to 5 to the 4, modulo 7. I'm going to explicitly compute these as well. I get 1, 5, 4, 6, and the last one I believe is 2. Okay, now we are actually almost done at this point. So this is where it's going to get a little bit funny.
Draw a grid.
Okay.
I think
Yeah.
draw like 2 axes.
Okay. Yeah, thank you, Professor Loh. That's actually a great idea. So we want the product of one number from the top, one number from the top, and one number from the bottom to be equal to 5. To be equal to 5 when we multiply them. One number from the top, one number from the bottom is equal to 5 when we multiply them. So, how do we do that? Well, let's draw a grid. On the top part of this grid, I'm going to have each of my remainders on the top. So what does that mean? Well, on the top, I'm going to have 9 lines, or sorry, 9 columns, and each one of those columns is going to be one of the remainders.
I
On
suggest
the
you sort them.
bottom,
I
oh, sorry,
suggest
what
you
was that?
sort them. I suggest you sort them.
Uh,
Well, sort one of them. Either sort the rows or sort the, so either sort the column labels or sort the row labels. It'll make your life easier.
oh, yeah, okay, that's true. What I'm gonna do is I'm going to actually sort, oh, wait! Yeah, wait, yeah, you're right. Okay, I'm going to sort both. Okay, you guys, hopefully everything makes sense so far, but I'm gonna be done in the next like 2 minutes. Okay, 1, 1, 2, 2, 3, 3, 4, 5, 6. And then here on my rows, I have 1, 2, 4, 5, and 6 as the rows. Okay, we want the product of a number on the top and a product, or sorry, we want the product of one number on the top and one number on the left to be 5 mod 7. The product of something on the top and something on the left is 5 mod 7. Okay, how do we do that? Well, hopefully you guys know your multiplication tables, and this step is actually quite short. We can just multiply everything out manually, and it's actually very short because all of the numbers are super small. So 4, 4, 8. And this is like what I really love about like doing a hard math problem is that at the end you can just like have some fun and goof off with something like this. But we just need to multiply everything out. And in the end, if I'm doing everything correctly, this is the grid we end up with. Now, what are we looking for? Let's remember what we're looking for. We're looking for a product that is 5 mod 7. So what does 5 mod 7 mean? 5 mod 7 means that the number I want leaves a remainder of 5 when I divide it by 7. So, what numbers leave a remainder of 5 when I divide them by 7? Well, this is a very easy question. 5, 12, 19, 26, 33. 5, 12, 19, 26, and 33. It turns out I don't need to go any more than this. Why do I not need to go any more than this? Well, because the largest number on the list is 36. The largest number in my grid is 36. Okay, so now I can just look at all the numbers in my grid and see which one of the numbers match this list of 5 that I have here. So let's do a bit of counting. I'm just going to shade them in with, let's see. Okay, I actually probably should have used different colors, so my apologies for that. But I'm going to use different colors now. So I see a 5 here. Let's see, where else do I see 5s? I see a 5 here, and I see a 5 here. Okay, where do I see 12s? There's a 12 here. Let's see, there's a 12 here. There's a 12 here. There's 12s here, and there's 12s here. Okay. Now 19 is prime, so I already know it's not going to be in this grid. It looks like 26 is not in this grid either, and 33 is not in this grid either. Okay,
I can save you a
so
little bit of time on that. Actually, for every row, there's exactly one residue because you actually, so 3 is what's called a primitive root mod 7. And so your column labels have all the non-zero mod 7s. So actually, because 7 is a prime, for any non-zero remainder, there's exactly one non-zero remainder you can multiply by to get 5 mod 7. So that's how you know you got everything.
uh,
Because in each of your rows, you correspond to you already got like one of the non-zero remainders, right? So look at the first row, the 1, you hit the 5. So it's like 1 and 5.
yeah,
Like 1 times 5 is 5 mod 7. 2 times 6 is 5 mod 7.
yeah. Okay, I think that makes sense. I was actually a little worried about that approach because there was something about Because I know like the exponents of 3, you get the first 6, and then there's a bit of a repeat after
That's
that
right.
with
That's
the
right.
1, 3,
So I
and
think
2.
that's why when you sort them, then you can look at it and you can be like, well, the row with the 5, that corresponds to columns labeled with 1. So I think
Oh,
what I mean is that it's actually, so technically speaking, what we're doing is we're doing 5 times the inverse of the row mod 7. So for example, the row with the
oh,
4, 5 times the inverse of 4 is 3 mod 7.
oh, I think I understand what you
You're
mean.
doing division. You're basically saying 4, if you're looking at the row labeled with 4, and I want to know which column, it's
Yeah.
like 4 times x is 5 mod 7. I'm solving that equation. And so the
Oh,
answer is x is 5 times the inverse of 4 mod 7. So there's exactly 1.
okay. Yeah,
But
so
that's too
for
complicated.
everybody listening just then, yeah, we were just talking about modular inverses
Yeah,
and
that's
some
too
other stuff.
complicated.
Yeah, it's too complicated for this, but basically, what I've done is I transformed this problem completely. I went from like step 1 to a completely new question to another completely new question, and then I believe that our current iteration, like this question that I have right here with this grid, was like iteration 4. And so at the very end, all I had to do was figure out the number of red squares in this grid, because every red square corresponded to a number that was 5 mod 7. How many red squares are there? Uh, you guys put the answer in the chat, I guess, if you're comfortable. Um, because I know I did not ask for much participation. How many red squares are in this grid that I've colored? 8, 8. Oh, 8. Okay, yeah, we got a lot of 8s. Um, all right. Let me ask you one more question because I do want to make sure that you guys understood things. Um, what does modulo mean? Give me an alternative word for modulo. I want to just make sure that you guys are understanding. What does modulo mean? And this will be the final question I ask you. Okay, remainder, remainder, remainder. All right. Okay, nice. Well, let's see if the answer is 8. If it's not 8, I'll be sad. It's 8. Nice.
Whoa! Oh my
Whew.
gosh.
Finally,
Okay.
let's go.
This
Wow.
was teamwork, by the way, because like I'll say I didn't know how to do this either, and as we were looking at it together, we were just brainstorming. Thank you to Alan Sheng for breaking the ice at the beginning, and for Alan Yuan for owning the board as we kept going. I do not know how anyone can solve 30 questions like this in 40 minutes. Uh, SM with
Yeah.
91 stars says this was the hardest problem. It took 35 minutes. We did it. Okay.
Do not
Well,
be afraid to skip on the real test, cause like there's a lot better ways to spend your time. But yeah,
yeah, Alan, thanks for sharing that. That's a really good point. I guess I'll just say I'm sorry we couldn't do more questions with you tonight, but I really enjoyed the opportunity to discuss these with you. It's always a lot of fun for me too because I like to challenge myself and I love to see how other people think. As you can see, Alan, they got something. They have great skills. If you like learning this way, you're welcome to continue following us. We actually do live solves on our channel, on our YouTube channel, almost every week. We do different levels of questions. Some of them are easier than this. Some of them are also harder than this. And of course, if you like this way of learning, actually, Alan and Alan are both instructors. They're both stars in our live program. We actually teach all of these math classes, all this MathCount stuff, actually in this style. Well, have a good night, everyone. We'll see you next time. Take care. Bye-bye.
Take care, guys.
bye
Enjoy
everyone.
your spring break if you're on spring break. I don't know.
Indeed.
Word. Word.